Hi everyone, this is Ihab Muhammad. In this video, I will speak about Model Predictive Path Integral Control Framework for partially observable navigation considering a quadrotor case study. First, I will give a brief introduction of our Clara project and what actually we need for performing autonomous navigation. Then I will speak about one of the related works, in particular MPPI and how it works. After that, I will give an overview of our proposed approach followed by the simulation results. Then I will conclude. In fact, this work is a part of Clara project, and the main objective here is to perform autonomous navigation of UAVs in GPS denied environment not mapped before, with the aim of finding missing people, fire detection and maintenance, and so on. Our main motivation here is to first propose a state-of-art model-based approach, followed by proposing a state-of-art deep learning-based approach, and finally propose a new approach combining both techniques. Indeed, having a safe and reliable system for autonomous navigation is highly challenging and partially solved problem, especially for cluttered and GPS denied environments such as forest, dark underground mines or warehouses, as you can see in these videos. So robots should be able to navigate autonomously while avoiding all kinds of obstacles in real time. To achieve complete autonomy, they must be able to first perceive their environment, then understand the situation they are in, and finally react properly. Generally, there are two main approaches that can be used for autonomous navigation. The first one is model-based approaches that have been used for a long time, offering reliable and well-controlled performance analysis tools. However, they rely on a simplification of models such as linearization, geometric sensors, and so on. On the other hand, we have a deep learning based approaches. For example, in end-to-end approaches, deep learning is used to control the robot directly from the perception signal. So from a single image, you can generate the control action. One of the good examples is DroneNet, in which the steering angle and the probability of collision can be estimated from a single image. The results here seem to be efficient. However, there is no analysis can be done between the perception and control, as we consider it as a black box. In this work, we mainly focus on model-based approaches. One of the promising approaches is MPPI, which proposed by William and inspired by path integral control theory. The key idea here is to sample thousands of trajectories in a real time from the dynamics of the system. Then each trajectory is evaluated according to a predefined cost function. All these trajectories are executed individually in parallel using a GPU. After that, the optimal control sequence can be updated over all these trajectories, as you can see in this figure. This optimal control sequence can be updated using this equation, where the cost to go of each trajectory equals the terminal cost and the running cost, while this running cost is equivalent to the state-dependent cost and the quadratic control cost, where nu refers to the exploration noise, which actually defines how aggressively the state space is explored. For example, low values of nu result in a rejection of many trajectories as their cost is too high. K and T refer to the number of trajectories that we are going to generate within a time horizon T, while delta U is a zero mean Gaussian noise vector, represents the control input updates. We can clearly see that this optimal method is a sampling based and derivative free, as there is no need for the derivative information to find the optimal solution. This actually one of the main motivations for us to use MPPI instead of using the classical MPC. This is the time to speak about our proposed approach. Actually, MPPI has been mainly applied to tasks of aggressive driving and UAVs navigation into decluttered environment, as you can see in these two videos. For that, MPPI requires the cost or the obstacle map of the environment. This map in most of previous works is assumed to be available and only 2D maps are used. Moreover, only the 2D navigation tasks are performed, which limits the applicability of this controller. For this reason, we propose a generic MPPI control framework that can be used for a 2D or 3D autonomous navigation tasks in first a fully observable environment. Here we assume there is a prior information about the environment or partially observable environment. Here there is no information about the environment and the robot is building and updating the map online as it moves around. And the key idea here is to provide the classical MPPI with a 2D or 3D grid which represents the real world for performing collision-free navigation. Assuming that this environment is discretized in a 3D voxel grid where each cell is labeled as a free, occupied, or unknown. One of the good examples in practice for acquiring the 3D voxel grid is OctoMap. So we can represent the environment by a set of layers where each layer represents a 2D occupancy grid. For example, for a 2D navigation task, only the first layer of the 3D voxel grid will be used by MPPI, while in the 3D case, the 3D voxel grid is required for performing the collision-free navigation based on the position of the robot. Let me speak about the simulation setup and the results. Here is the Quadrotor dynamics model used in our simulation. It has 12 states. The first 6 components define the pose of the vehicle, while the rest define the linear and the angular velocities. The control signal here is equivalent to the accumulated force generated by all the rotors and the total torque applied to the vehicle. The running cost function of each trajectory has the following form, where the second term is used to penalize the collision with ground or obstacles, while the third term prevents the drone from going too fast. Here are the parameters of MPPI that we have set during our simulation. Here, each 20 milliseconds we generate 2,700 trajectories within a time horizon of 150. So we tested our framework on a set of goal-oriented 2D and 3D navigation tasks in cluttered environment. Assuming that first, we have the map of the environment, and this is a fully observable case. While in partially observable case, we assume that there is no such information and the robot should build and update the map as it moves around. Here we define the 2D scenario for the 2D navigation tasks, while the 3D scenario for the 3D case. We set the voxel size to 20 centimeters, which means that the 3D voxel grid to be used by our controller has in total 43 layers. So to test the overall performance of our controller, we perform 5 trials for both cases. The results over these trials are given in this table. Here we use a number of indicators to measure the performance of our controller. The first one indicates the number of collisions and the task completion percentage, while the second and the third one refer to the average flying time and the distance, while the fourth one refers to the average flying speed. We can clearly see that the robot is able to navigate safely in the cluttered environment with an average speed of 1.2 meters per second, which is closer to the maximum predefined speed, which is in our case 1.5 meters per second, regardless of the limited field of view of the sensor in both scenarios. The last indicator refers to the execution time of MPPI per iteration. We can see that it's less than 20 milliseconds, which means that MPPI can be running in real time even with the 3D voxel grid. Here I'm showing the simulation results of a 2D scenario in partially observable case. On the left side you can see the trajectory of the robot. Here we defined 4 targets to be reached with different altitude. On the right side you can see the updated map by MPPI, which is the one in red, and the set of indicators. Here are the simulation results in the 3D case. Given the same targets, it can be clearly seen that the drone navigates safely in this cluttered environment without any collision. In this work, we also studied the impact of changing the time horizon and the exploration variance, as they play an important role in determining the behavior of our controller. For that, we consider 6 different tuning cases. In each case, we perform 3 trials. In the first 3 cases, we studied the influence of changing t where nu remains constant. We can clearly see from case number 1, where a short time horizon is chosen, that MPPI is unable to complete the trial at a satisfactory rate. In the last 3 cases, we studied the effect of changing the exploration variance nu. From case number 2 to 6, we can observe that the MPPI performs perfectly and it is able to successfully complete all trials while avoiding all obstacles. We can also notice that as t and mu increase, the performance of our controller improves. This can be clearly seen in case number 3 and 6, as the average flying distance is the shortest comparing to other successful cases. However, having 2 long time horizons increase the computational effort as each trajectory takes more time to be simulated. Also, if nu is too large, the control generates control signal with significant chatter. Let me conclude. Within this work, we propose a generic MPPI framework that enables the robot to navigate autonomously in 2D or 3D partially observable environments. The key point of our proposed approach is to provide the classical MPPI with a 3D voxel grid for performing collision-free navigation. Our framework has been successfully tested on a Quadrotor case study. However, it can be used for other types of robots. To ensure a realistic simulation, we evaluated our framework taking into account the modeling errors, noisy sensors, and windy environments. The current simulations show the robustness of our proposed controller for both 2D and 3D navigation tasks. Our future work directions will include first the implementation of our framework in practical application, taking into account dynamic obstacles, then exploring the possible methods that study the theoretical stability of MPPI, as up to now only the practical stability is achieved by tuning properly the parameters of MPPI. Thank you for watching.